All right. So hi everyone. As you probably noticed, there's like an announcement about how to sign up for groups for the project. So we need you to find a group by maybe say tomorrow at like 11:59. If you can't find a group, we will help you by just sorting you randomly. So if you want to be in a group that you decide, you have to get that set up by tomorrow night. And the way you're going to do that, the instructions are all online, by the way. But you can do that by going on Canvas in the I think it's called People tab on the side. There's and if you click on it, there will be another tab on the main page that says Groups for Project One. Click on it, and then there will be a bunch of groups. And go ahead and just drag your name under one of the groups that are empty and have everybody in your group do the same thing. And that's how you're going to basically tell us which groups you're in. So if you don't do that by tomorrow night, then we will just assign you randomly. So no worries if you can't find people. We will make sure you have people. And then you have to submit a summary of your project. It doesn't need to be long, just like we just want to make sure you're on the right track by, I think it's Monday night.
Sure.
Or sorry, Monday morning. It was by 11 a.m. on Monday morning. And it's just short on Gradescope. Just make sure that when you submit it to add everybody in your group to the assignment, so only one of you has to submit it. That way, you don't have to submit it 4 times or 3 times. Does anyone have any questions about the project? Yeah.
How flexible are we with the number of people in the group?
Ideally, we have three so that it breaks out to presentations. We have so many people in the class and we need the right number of presentations. So if there's some really serious reason why you need two or something, then that's fine. But
Also, if you sign up for a group and only like 2 people are in the group, I will add a third if you don't have one by then. So we're gonna really try for threes because that makes it the presentations like you could have them a little longer. If we made the groups any smaller, we couldn't actually present that many people. So
okay. And the summary of your project is just what the topic is, right? And what you plan to do, like we're going to do a MATLAB simulation of the following or something like that. So that if everybody comes in with the same topic, we're going to come back and say, we can't all do the same topic, right? We're going to limit like 2 groups per topic or something like
I also
that.
think there's a Google Sheet also linked in the document that you can sign up for the project. Like you go give a project topic there, just so that you guys all don't like accidentally take each other's projects and then have to change
Right.
after Monday. So that's kind of to hopefully prevent that.
Great.
So please check that first, and we'll go by whoever posts it first. So if it's already posted, please don't post it again because then I'll have to figure out who posted it first, which I'm not entirely sure how to do that.
Okay.
I think it's in the edit section or in like the tracking section, but any other questions? Yes.
Along with our own topics. So
yes.
Does it have to discuss like with you guys before this week?
Oh, well, submit your own topic, which is fine. And then if when we search through it, we say, well, I'm not sure that really is on point or that's going to be useful to the class, then we'll come back to you. But yeah, just give it a title and a description. And I'm fairly confident most people will pick a topic that's on point. So
I think mainly it's just when it's duplicates that we have problems, not so much that the topic isn't like good enough.
Yeah.
Any general guidelines to know if a proposed topic is a good one or not?
I think they're mainly listed on the documents that was provided. I don't know if
there's like 12 examples or something there, so you get an idea of the gestalt of what a project is. But if you come up with your own, that's great. I mean it's something that we think the class would be interested in, and we're interested in exploring more. Then that's terrific. Yeah.
All right. Cool.
All right, great. Thanks, Katie. All right, this is where we left off on Monday. We're going to skip this because it's not that interesting. This is the basically setup that Hounsfield used to perform the first CT scans in history when he invented it and produced images. And he actually didn't use an X-ray source. He used a basically something that radioactively decayed and gave off gamma rays, essentially. And so they came out of here, and then he had a scintillation detector here. So he looked at the absorption of those gamma rays along this line with the detector, and then he rotated this platform to get the different views. And well, he did two things, right? He translated the platform across to get different views along one angular view or different projections through the sample. And then he would rotate the platform and do another translation. Okay. So that's how he did that. Took hours, to actually scan through and get all of that data. Early CT scanners had X-ray source like the following, and it would translate across the patient, and there'd be a set of detectors that would translate with the source. Now, the classic geometry is you have one X-ray source here, a point, and it has a fan beam of X-rays out here to a set of fixed detectors that are fixed with respect to the source, right? And then both of the source and the detector elements rotate, and you get different projections as that rotation occurs. Modern CT scanners usually have more than one slice at a time. It started out, 20 years ago, somebody made a 4-slice scanner, and that was a big deal. You increase your efficiency by a factor of 4. Now this has gone up to as many as 320 detectors on it's the Toshiba or the Canon scanner has 320 slices. So that's a remarkable increase in efficiency at collecting data. And so here's our geometry. Here's the X-ray source up here, right? And then this is called the fan angle for the fan beam itself. This is called the cone angle because explicitly we're doing cone beam CT. And we're not going to go into the math of cone beam CT. We're just going to pay attention to the center slice, basically, when we're doing the math of how to reconstruct CT. But there are multiple detectors in the Z direction of the slice direction in modern scanners. A couple of ways to acquire full body data when you have this setup. One is you rotate the detector and the source around a single slice, and then you step the patient along with the table, and you do that again. And step the patient along with the table and do it again. And that gives you multiple slices as you're going through the patient. And you can imagine if your detector has, say, 8 slices, then you can make a bigger step and do another rotation and then a bigger step as you're going through. And so that speeds things up. If you really want to go fast, you can do what's called helical scan. And what we'll do is we'll just get the source and the detector rotating at a constant frequency, right? And then we'll just move the patient through there continuously. And we'll collect the data on essentially a helix. And for any given slice, we'll have to interpolate between where the data was obtained as it went through, the timing of that position, right? So you'll have, for a particular slice, you might have something was sampled over here in time, something was sampled over here, and you interpolate those 2 points together. That's something that Siemens originally came up with, and they jumped ahead in CT technology when they did that. And the big deal there was normally your detector's down here, and you have all these cables coming out for the signals, right? And then they would rotate the gantry, and all the cables would rotate with the gantry and stop. And then you'd have to go the opposite direction because you couldn't wind these cables continuously, right? They would break. So what Siemens came up with is slip ring technology, where all of the electronic connections between the detectors that are rotating here and the computer that is in the control room, all those wires were connected electronically by a set of brushes and essentially copper circles. And so those brushes just went around as the gantry went around, right? And this was a huge increase in efficiency because not only were you not limited to going 360 and then coming back, you could then start spinning this thing at an arbitrary rate, right? So you just start it spinning up and keep accelerating it until finally something flies off and okay, we can't go that fast, right? You put it back together and you just do it until you're mechanically able, right, to hold on to everything. Obviously, if we spin it super fast, we're going to zip by these projections really quickly. So that puts a strain on our X-ray source, right? Because if I go 5 times faster, I need 5 times more X-ray fluence, right? In order to get all of those projections with enough X-rays. And so the tubes get more and more powerful. Siemens did another clever thing. They put 2 X-ray sources in the gantry and a detector here and a detector here. So they increase essentially their angle of sampling, or they basically got 2 CT scans done at the same time at 90 degrees, right? So basically they could get the data twice as fast with that as well. So this is a movie of what a modern scanner looks like. This is the GE Revolution scanner. That's about how fast it rotates. It's pretty impressive. We'll see some YouTube links where engineers take the skins off and like with their handy cam, they film these things spinning. It's pretty good. And then here's the detector X-ray source up here. This is the power for the X-ray source. It generates the voltage across the X-ray tube. You can select the volume you want interactively, basically, if you want a thinner slab, etc. And then we took a look at these detectors last lecture. This is what it looks like when it was getting installed at our place. This is in 2016, I think. So it's a lot of hardware here that spins, right? And as I said last lecture, this hardware is under 80 Gs when it's at its maximum spinning rate. The other engineering thing you have to do is make this thing spin quietly. If you're spinning something that fast, it tends to make noise and sometimes tends to vibrate. And like your washing machine, sometimes when it's not balanced properly, like you get this big vibration. That's why General Electric can make these things, right? Because they make dryers and washing machines and jet engines, right? So when you're spinning that thing, you don't want any vibration because that's going to screw up the image. And the noise you want to keep down because that interferes with the patient's comfort. They start to get anxious, right? When they're in something and this big spinning sound happens, right? So you have to give them Valium at that point. So here, look at this YouTube here or this one, and it'll show interactively how they took the covers off and just started the thing spinning. This used to be a great YouTube video. It's gone now. So and they replaced it with this, which I tell you what, it's AI makes some things that are really good and some things that are really bad. Right. And this one's obviously AI. They have AI generated music, like it's classic, generic music and all. And then this thing, they show it functioning, but it's like in orbit around the sun. But the sun is blue and it has just like, what is it? So some things AI should just leave alone. So this is the Siemens structure. You can see this detector is a little bit bigger than this one just to make everything work out, but it's really fun to watch this thing spin too. So here's a little video of how you spin up the gantry and then you put that patient through at about that speed, right? So it takes about a second for the patient to go all the way through. Here they've slowed it down. The pitch is higher. That means they're overlapping their views more. And so it's fantastic for getting large field of view images very quickly. And this is CT usage, probably from Medicare data or something. I don't know what the data is from, but it doesn't really matter. It's just relative numbers. Through the 80s, basically, CT started, it was useful and everything, and people used it a lot. But then as soon as helical CT came up, the usage changed its slope, right? And it started getting adopted even more quickly. And then once multi-slice started, so now you get a 4-slice scanner, here you get a 16-slice scanner, here you get a 32-slice scanner, and so it just keeps going up and up and up. And in 24 now, we're up here at 320-slice scanners, and there's like 100 million CTs done a year in the US, right? And that's a big number. Like there's 350 million people in the country or something. There's 100 million CTs done a year, right? So it's a significant number with respect to the number of people that are here. So it is obviously also a significant source of radiation dose in a population, right? Because that's a population. 100 million is now a population, right? So if you ask, well, I'm doing this 100 million times, and this is a random event that causes some kind of DNA strand break and then goes to a cancer. Is this causing many cancers in the country? Because it's a significant source of radiation. And so papers were written usually about 15 years ago that are quite controversial, saying, oh yeah, at least 4,000 cancers a year are caused by CT scans, right? Because there's so many people getting these scans. However, the statistics of that is very, very difficult because you're working with a signal that is tiny, right? So your increase in risk is minuscule. And so to say you know what the increase in risk is at really low doses is not that valid. So it's a really interesting scientific question, though. It's like, how do you measure this, right? It's a hard thing to measure. This is a chart, just you can look at this on the PDF, but it's sort of generations of CT, how the engineering has changed over time until we finally get to this multi-row, detector CT. I mean, that's called the 7th generation. We looked at this detector geometry already. Remember, this is the anti-scatter grid. These are our little chips that have the 1 by 1 by 1 detector on them. And then this is the anti-scatter grid when you, can I play this? Oh yeah. So this is in the exhibit case at General Electric. And so let's take a look at this signal right here. We're looking straight down the anti-scatter grid. And then if you look at a very small angle away, it just goes away. That thing goes away. It comes back again because this is light, and so the light is reflecting up the path, right? But if it's an X-ray, it's gone, right? So there's basically only one angle that thing can look through. And I think that I might have gone the other way too. Well, you get the idea. Okay, so here's the source of our X-rays. Here's our patient lying in the scanner. This is called an axial slice through the patient. It's just, you lay them down, cut them like that, like a saw, like they were a log. Okay, so this is the heart, spine, etc. X-rays are going to move through space along lines and hit the detector or not. And X-rays that get absorbed in the patient don't hit the detector, and X-rays that just make it through hit the detector. So if you look at the X-ray intensity as a function of position along here, this will be called L, or you could call it detector number, as a function of position along here, we see that the X-ray intensity is very low for the X-rays coming straight through. And the reason for that is they hit the sternum, which is bone. They hit the heart, which might have contrast in it, so it would take out even more X-rays. Then they hit the aorta, which also has contrast in it. Then they hit the spine, which is bone. So there's a lot of ways for that X-ray to get absorbed. So when you look at it, not many get through on that trajectory. If we look over here, the X-ray didn't hit anything. There's nothing in its path. So it's a clean shot to the detector. So you get the maximum number of X-rays in that detector. That's an important number, and we'll measure that number every morning on this scanner. It's just like, if I had air in here, if I took the patient out and just went poof and put X-rays, what would that number be that hits here, right? So we'll see in the math, you need to know that number, actually. So they measure it every day. Now we'll rotate the source, and the plot of the absorption just shifts along with that rotation, such that now if I look down through here and say, well, where do I get a deep attenuation of X-rays? It's wherever I'm hitting this spine usually. It gives me the deep attenuation over here. So that feature moved over to that position. And now here I have a lot of beams that are just hitting the detector clean. They're not passing through the patient at all. So I have many that are at this, baseline value of X-ray fluence. Here's how, I showed you Hounsfield's setup. This is a friend of mine, Webb Stamen, he's at Hopkins. And this is how you build a modern benchtop CT. You get a really nice high resolution detector panel. You get a very good X-ray Okay, so this is a modern day benchtop CT, and here's the object we're imaging, and you can put it on a really intelligent computer programmable stand for, such that you can rotate it while you're taking these images. And you can rotate it in any arbitrary way, right? So it sort of generalizes to a 3D rotation as opposed to just a 2D, but it makes really good pictures. So here's the speed up in CT. Remember when we saw that first image, which was 80 by 80 head, and it took 20 minutes. You got two images and they looked like this. Granted, you saw something you couldn't see on a plain film, right? So it was worth it. But it also was like, 10 times, 100 times more expensive than a plain film. And it took, 10 or 100 times the radiation back then to make the picture. So investing in this was a bit of a stretch, right? But there were believers and they kept going, right? Till finally you get here in the modern day scanner, you have 320 images. They're 512 by 512, and you get them each. Actually, I think you get them at 170 milliseconds, right? So, over that course of 30 or 40 years, it underwent some pretty cool changes. And this is Norbert Pelk actually went back and got data at each epoch. He's been in this since about here, right? And how fast scanners were going, and he plotted out that, and just in terms of pixels per second. And then the black line is Moore's law, right? So it just basically goes up with digital, processing with it, and some engineering. X-ray tube power, obviously, as you get faster and faster images, you need more and more X-rays per unit time in order to have enough X-rays in each image data collection, right? And so that pushed X-ray tube technology up here. You've got a 100 kilowatt tube. This was in 2010. That's doubled since then. We're up around here now with these tubes that produce, 1,300 milliamps, at 80 kV. So this has been a huge engineering achievement as well. And there are multiple designs of X-ray tubes that achieve this. So yeah.
I think machine that is already evolving so fast and it has to withstand like 80 G of acceleration.
Yeah.
Must have its own set of complications. But why does it have to spin so fast? You can just, rotate once, move, rotate.
Yes. It's a great question. So the question is, it's a really general question, big, deep question, which is, why do you have to spin so fast? Why don't you just use a lower power tube and spin the gantry at a reasonable rate and get one image per second or something like that? And the reason is the human body moves, right? So if you're imaging a heart, right, then if you take 1 second to take that picture, you just get a blurry picture of what a heart averages over 1 second, right? Secondly, if I want to image from the top of a patient down to their, like beyond their pelvis and get all the vascular structures from here down to their knees, I need to move them through the scanner such that the contrast that I've injected is still there when I'm taking all those pictures. And so if you step and do 1 second, 1 second, 1 second, it's gone, right? The contrast stays there for about 10 seconds. So you need everything done. And ideally, the contrast has the same value in the whole volume. And so getting it done quickly is an advantage. So it just pushes things higher and higher. But cardiac and breathing, things like that, if you have to breath hold, it's another thing that the patient has to focus on, doing a good breath hold over multiple times, etc. So faster is just better. Okay, so let's review the attenuation model for X-rays through matter. If I have a distance d through some stuff like water or muscle or bone or something like that, and I have an intensity of X-rays going in, the intensity coming out goes by this very simple decay function, right? The mu value is obviously the number of E values per centimeter that, the X-rays will diminish by. Okay, so it's a really nice, simple solution. And we talked about this before, how this cascade of, different depths gives you this exponential decay. Let's keep going. Okay. So I think I put this in here because we changed notation. So here's the number of photons hitting the patient's chest, say, and this is the number of photons coming out of that patient if we integrate from 0 to X, where X is the depth through the patient, right? This is the intensity. It's equivalent to saying the intensity of the X-rays go in. That is, what would hit my detector if there was no patient there? That's this number. And then this is what hits my detector when there is a patient there, that intensity. And it's still this simple integral of all the mu values as I traverse through there. If you want to model this absolutely precisely, you need to take into account the energy of all of the photons, because you have a spectrum of photons, not just one energy. And the importance there is that the mu value is actually a function of energy, right? So that's depending on what enters a voxel, in my object, what the energy of that photon is, the probability of it getting absorbed is dependent on the energy. So this, complicates matters. So we just ignore it. And we say, let's do everything at the average energy. Like all of the math that we're going to do from here on is going to just assume we have monoenergetic photons at the average of that density, right? So to set up the math, this is in your textbook as well. We'll use a coordinate system that looks like this. We have the two-dimensional plane. Again, it's like the cut in the log that we have. So it's an XY plane on there. And our function that we're trying to extract, right, is given as this continuous fxy here. And we are going to take projections, or we're going to look at the trajectory of photons as they come to the patient, hit the chest, have a probability of being absorbed as they move through the patient, and then a certain number will come out, and it will be less than went in, right? There is no way that in CT, we have observed that when we put X-rays in, more come out, right? And then we're going to detect them along the geometry of our detector, which will have a parameter called L, which is that geometry. This angle is parameterized by an angle theta, okay? So this line here is a set of X and Y values in the plane such that this relationship is true. And we looked at this 3 lectures ago, I think, as the function of a line, of a delta function line, right? You can, if you want, you can rewrite this as y equals mx plus b. It's just the equation of a line, right, in the plane. But it's a different way of writing it down such that L, which is our parameter here, is in the equation, and theta is in the equation, which is our angle, okay? And so this cap L theta are all of the points along this line, okay, mathematically. So here's our energy spectrum. Here's the complicated thing. We're going to say monoenergetic assumption gives us this equation. Instead, all of that energy just goes out to say we're going to have a mu value, which is the mu of the average energy, is what we're going to solve for. It's not precisely the mu value of the average energy, but it works out to be pretty similar, most of the time. We'll see sometimes when it fails. And so this is our detector intensity, and this is the intensity that hits the patient's chest. So what I can do is this number, ID divided by I naught here, we know that's some number between 0 and 1, right? So let's take a look at that thing. We'll take the negative log of that such that, and it's obvious why we're taking the log, right? Because this thing's an exponential. Take the log of that, all you're left with is the integral. The exponential goes away. Okay? So this, when we do this operation on our data, we've measured these. We measured these this morning on the scanner. Take the log, have a negative sign because it's 0 to 1. And we get this thing GD, which is just the integral of those attenuation coefficients, which is really cool. That's a big step, right? Now we just have a sum. Basically, if you think of an integral in its, discrete form or a finite form, and I've got, 500 voxels, I just have the sum of the mu value in each one of those voxels, right, is equal to this thing. Is my measurement, basically, right? So that's a big, concept. Everybody understand that? That now we'll look at it in some detail, but I can basically look at my raw data and say, oh, okay, that just represents the sum of all of these mu values as I go through here. Right? So here's our geometry again. N naught or I naught intensity hits the patient here. I get absorption. It depends what I'm going through, how much absorption I get, and I sum it up as I'm moving through here such that when it comes out the back of the patient right here, I get this intensity coming out of the back of the patient, right? And now I do this algebra to get a number that is proportional to the integral or the sum of mu values, and I plot that thing. And that's going to be a number that's positive, right? Yeah. Mu is for each tissue, you ask, well, how many x-rays get absorbed per unit length through the tissue? That's what mu is. And so mu for water has a specific value. Remember, we have those half value layers, things like that. So that is described by mu. And it gives you the number of E decrements in your number of x-rays per unit distance.
So in a single frame like this, it's adding up all the mu's across all the tissues you encounter?
Correct.
Okay.
Right. It's just a sum of all those mu's, which is pretty nice, right? It's pretty simple. Yeah. Well, the raw data that we measure on our detector is ID. That's the intensity we measure on the detector. And then that morning, we measured I sub 0, which is how many photons we would have measured if there's nothing there. Okay. So this is without the patient, and then this is with the patient. So now I have a relative number, from that's basically normalized to the sensitivity of the detector and everything, right? And then I take the log of that. This number is between 0 and 1, right? Say it's 0.5, 50% of the photons are gone. Take the log of that. That gives me a negative number, right? I take the negative of that just to get rid of the negative number. And GD is now a positive number that is proportional to the sum of all the mu values. Yeah.
So that one GD is plotted on that L graph down there?
That's correct. And then I have a G at each point along here for L. So this is a map of, GD as a function of my position on the detector. Okay. So we know it's a positive number, right? So things are going to get complicated if this intensity goes to what number? 0. You got a mess, right? So you don't want that to happen, right? And you don't really want to even be close to 0, because if you have 1 or 2 or 3, then that number, that log of that number gets really big, right? Because this number is like 10,000 or something, or photons. And this number, if it's 1, now you got a very large, remember what log looks like, negative log, right? So got a big number. So you don't want that, because you'll get really high noise values when this is a very small number. So here's an object we put in the scanner. It's an hourglass shape that has contrast in the center cavity of the object. This is just some material that we use to print this shape. These are leads, pacing leads that we just tape to the side of this object. You can see they're very bright in a CT scan. The contrast is bright. The this stuff, middle of brightness. So let's look at what the raw data looks like. Okay. To make that image, these are the projections that we see. So this is one projection. And what we're going to do is we're just going to plot all those projections as we rotate our source and detector around the object. And you can see it looks just like an object rotating, right? That's exactly what it is, a shadow of an object rotating, right? And so if I go back and forth, like let's look at this angle, you can see the patient table right here, right? Because we're direct on line to the patient table, so there's a lot of absorption at that point. When we go orthogonal, there's the patient table, but we're looking right through the thin part. And there's a couple of other things to observe. One is there's very bright background here. Obviously, the X-rays aren't hitting anything, right, in this projection right here. And so I get a GD is a very high positive number. As I move away from the center of the scan, it seems to get dimmer and dimmer. And you're like, well, why would it get dimmer? There's nothing out there, right? And the reason it gets dimmer is the manufacturer puts what's called a bow tie filter that lets more X-rays go through the center than through the periphery. And the reason is that if most of the time when you're imaging, say, somebody's heart, you don't care about signal in their right arm or their left arm. So you can attenuate the photons out there and just have, a larger fluence of photons in the middle, right? So that's what that is. That's called a bow tie filter response back there. And then we've got enough angles to reproduce this object. And in 3D, it looks like that. Okay. This is now, that raw data has not been logged, right? So the intensity, this is just pure intensity data we're measuring here, right? So the intensity around this pacing lead is quite low because it's a metallic object that is absorbing a lot of X-rays. And so on the detector, we see a low number. And so this is that number, right? We haven't taken the log yet of that stuff to do the reconstruction. Yeah?
GD, does that have like a physical meaning, I guess? Or
Yes.
is it something that we define?
No, it has an absolute physical meaning because so the question is, does GD have a physical meaning? And the physical meaning is it is the sum of the attenuation coefficients along a line, right? So those have a physical meaning. I can measure those, for a substance. I can say, what is the mu value of water? I can measure it. What is the mu value of fat? What is the mu value of muscle? What is it of cortical bone? So I have all of those mu values. Those have absolute physical meaning. They are in a catalog at the National Institute of Standards, right? And so GD is the sum of those mu values across the projection line. That's its physical meaning.
Question, sorry.
Yeah.
In this picture, where's the source and where's the receptor?
Oh, the receptor or the detector is this thing here. It's a two-dimensional. It has 256 detectors in this direction. It has 832, I want to say, in this direction. So it's a two-dimensional detector grid. And then, so that's what I'm looking at. And the source is, if I pull that back to my nose, my source is here and it projects through that way.
This is like being standing.
And looking from the source down at the object, yeah.
Okay.
Yeah. Now, you could equally well look at the detector from the back and you would get an image of 180-degree inversion of that object, right? So I believe this is from the source to the object, is what I believe is displayed. Yeah. Now, we can check that though. Let's put something in the scanner and we can see like which direction. If I put an object in there that isn't symmetric, say which direction is it? Yeah.
So GT, I guess, and the intensity we're seeing here right now, because I mean, the intensity is technically the sum of the, as you're saying, sum of mu, and thereby,
No, the intensity is not the sum of mu's. GD is, because after you take the log, that happens.
then it's my mu is just I want to say the measurement of how many rays are not hitting the detector.
No, mu is something that is tied to the material that the X-rays are going through. That's it. Yeah. So if you have a very high mu value, not many X-rays get through, right? If you have a low mu value, many X-rays get through. And so that's what mu is. And so it sits there, it's fixed. And then what we measure is the change in the intensity of X-rays at the detector. And we can measure that. And so the X-ray detector, the intensity is lower here than it is here. So that means two things. Two things could cause it. It's gone through more stuff, right? Or the stuff it's going through has higher mu values. Yeah.
But then I don't understand well the range of values that mu can take.
Yes.
But I guess there are some mu values that completely block.
Sure. Yeah.
And if that's the case, if we stack that material one after the other, G wouldn't be the sum, right? It would just be the max.
That's right. So the question is, what happens if mu is so high that, let's say the person is laying in there and they have a medallion on their chest or something. And then when you project through the medallion, all the X-rays are gone by the time it comes out of the back of the medallion. So all you get is 0 on the detector. You're kind of screwed, right? You can't make a picture at that point. You have to take those views out of your recon and say, you know what, I'm going to replace those views with something sensible, because mu doesn't work. 0 doesn't work as a data point. Yeah.
D is like basically the small d.
Oh, yeah, it's the limit of the integration. Yeah.
Boundary, that's something we don't know the boundary.
Well, we're going to figure it out. But so we could say D is the distance between the source and the detector. Okay. And that way, D is always the same. It's just how many photons hit that detector. So the boundary will come out as a mu value, right? You have mu of air around so you solve for that too. Okay, good. You guys asked like an order of magnitude more questions than any previous class, which is very good. Right? That's right. It's like 10 years of questions have been saved up for these lectures. Okay, but it's great. I think that's very good. It shows where we should explain more and what's confusing. Okay, so when we look at this, we're no longer plotting I, the intensity that we see on the detector. We're going to take I, divide it by I naught, and take the log and the negative of that, and we'll get positive numbers. So at each point here, I have a positive number, and that is the sum of the mu values that were along the ray that went through that distance, right? So we got a lot of sums here, right? And we've got 256 by 832 sums, and in each one, if I want to reconstruct it, say with 512 by 512, I got about 500 sum, a sum of about 500 mu values as I'm zipping through there. So each one of those numbers is the sum of many numbers, right? The problem gets pretty big, right? So, and the brightness is, it's more intuitive, I guess, to say, well, where it's really bright, I've got a lot of attenuation. Now, you can see at these borders here, like we're out of the threshold, but let's look, this is a person's chest, obviously, right? It looks like chest x-rays of a person standing on a rotating thing, right? What you could do if you want to make a really cheap CT scanner, you get a chest x-ray machine and you get a Lazy Susan. Do you ever know what the Lazy Susan is? Like from maybe a Chinese restaurant or something like that, a big one that can have lots of stuff. Put them on that and just spin them, right? And just take a bunch of chest x-rays, right? And then that's it. You got a CT. It's not going to look great unless you do some, machinations, but it'll be okay. But when you look here, this is what I want to show you. So now we're looking through the patient's arm, through their chest and through their other arm, right? Or their arm might not be there. They might have it up here, but we're going the long way through the chest, not, through the front to back, going a long way. So this is their back, and it's going through tissue all the way, right? It's laying on the table. And so you can see how there's like this sort of hashy noise there. Like some of the pixels get really bright because the photon count is getting dangerously low to 0, right? And so that negative log of something that's really close to 0 becomes a very large number. And so that is a problem. And so the amount of noise, the uncertainty in measuring how many photons you've got there gets really high when the number is low, right? Out here, when you have more photons, there's a rational way to describe what the uncertainty is in that measurement. Yeah.
So raw data, like the intensity which the delta sees, or is it like scattered, corrected, or is
This that's a great question. So the question is this purely raw data in that, or has it undergone some other high level correction? Right. That is a great question. And my answer to that question is I believe it has undergone all those corrections. Because normally when you take raw data off your scanner, if you're inclined to hack in to machines and grab raw data, right, you're going to get something like this, right? And it hasn't gone through all of their processing, and they're not going to tell you how they do that, right? And the reason they don't tell you is because they make corrections for shortcomings in the machine. Like they have to interpolate here, they got to average there, they got to do this, they got to do that. And or they have some magic way of say correcting for scatter or for energy differences, stuff like that. And so they're very secretive about how they turn this into this, right? And so you can get this. This is a program we got from Canon to just take the raw data and give us sinograms, right? So this is all corrected. Yeah. Mm-hmm.
So this image isn't just like a sum of the mu's as opposed to like the previous image, like.
Yeah, it is.
Okay.
Yeah.
So isn't that how you would get from the intensities to the GD values?
This is the GD values. Yeah, these are the GD values, right? So these are the sums of the mu's.
So the GD is like kind of like a filter to almost kind of like a filter to like make the intensity better, or like.
No, I'm not sure I wouldn't call it a filter because it doesn't really smooth anything in space. It's an algebraic expression, that you can write down an algebraic expression for what it is in terms of the mu values on each path, right? What we're going to do, though, is this. Remember, this is slice in this direction. So Z, the patient's head's up here, their feet are down here. This is their diaphragm, their heart, you can see here. So all of the math we're going to do now is how do I reconstruct the plane that this red line would cut through, right? So we're going to go back to that two-dimensional plane. And this gets back to your question. These are like the chest x-rays. And now I'm going to take one line of data here, right? And I've got all these chest x-rays of the spinning patient. I'm going to take one line of data. And those will be my GL theta for that plane. So I have that for many lines, but I'm going to ignore those other lines. right? And we're just going to look at one. Okay. So we'll go back to our original cartoon where we put all these variables in context, and we'll go through it one more time just for grins. N naught photons are coming with an intensity of I naught, hit the patient right here, right? And then it goes through a whole bunch of different mu values as it goes through different tissues, right? And it gets attenuated by that mu value in that volume as it's moving through. And then a number of photons exit the back of the patient. And that's the intensity ID that comes out of the back of the patient. That forms that shadow, right? And we looked at that shadow in that phantom, right? They directly looked at that shadow. However, instead of looking at the shadow to reconstruct the image, what we'll do is we will take our measurement from this morning that tells us how many photons would hit the detector if the patient wasn't there, right? How many photons hit the detector now that the patient is there? And we'll do minus log of that to get GD. And that's a positive function. That's that brightness function, right? And we're going to do that at, say, 1,000 or 500 different angles. So you saw the angles just spinning around, and we just get those at each angle. So the G now is a function of L, which is a position on our detector, that one-dimensional position on the detector. It's also a function of theta, right? So if I fix L as I change theta, I'm going to get different values. So I have a two-dimensional function now. And so my two-dimensional function is just GL theta, right? And that's what it is. It's a two-dimensional positive function in the plane. That has the equivalent information of mu xy in the plane. Because this was created by a whole bunch of different sums of these things, right? That's why it's equivalent, right? But the trick is, how do I change this thing into this thing, right? So that's CT image reconstruction. It's like, how do I change this set of projections, right, of relative amounts of photon absorption and the sum of all these mu's into a map, a 2D map of mu? And this is our CT image. When you look at the CT image, that's what you're looking at, is this thing, right? Okay. There's a number of you will be asking, well, you know, if I look at the geometry of this thing, L looks like it's flat. This line that we've, parameterized here as a function of L and theta seems to be a straight line, and all of these L's would come from parallel lines. They'd all be lined up in a parallel direction. That is true. Yeah. I'm sorry, say is the log detectable? Yeah. Yes. Yes, absolutely. The reason the log behavior is in there, it's really the exponential behavior that's there. The exponential decay is what is happening but when you take the log, you get rid of that exponent and you just have the sums of the logs left over. That's what turns it into a linear algebra problem versus a nonlinear problem, right? So, so the question now is like, well, I now could do this for a whole set of parallel rays. I could set up GL theta, right? That's what this math that we've set up here, would say we do. So it looks like this, right? We have these parallel beams. We have, for this one, let's parameterize theta. We'll say it's 90 degrees for this. And here's L along here. And for my theta equals 90, I will measure each readout, each, GD theta along L, and it'll map this way. So here's L and here's theta. So I'm creating GL theta by drawing vertical lines in this two-dimensional plot. Okay. I changed the angle to 120 degrees. I still have this, So at 120 degrees, I map out those measurements again. So in this way, I'm going to fill in GL theta on a 2D plane, right? Just by clicking through those angles. Well, how does that work with a fan beam? Because this is the actual geometry we use. We have a point where the X-rays are coming out of, and then they come out at different angles, right? So these, when I detect one thing, I say, now I have a detected amount that I want to put into GL theta for each detector along here. Where do I put it in the GL theta space, right? Because it's now I've got a lot of thetas along here, right? And so where you put it is you say, well, if my center one is at 90, let's label this projection as the angle of the center one. So that's at 90. Then some of the measurements I make will be at lower angles, and some of the measurements I make will be at higher angles. And so here's the ones at the higher angles, or which 120? Okay, here's the ones at the higher angles, and here's the ones at the lower angles. And so that's how I map them into GL theta here. Is that clear? Yeah.
Between like G of L theta and then like capital L theta. Because it seemed like in the previous slides, like capital L theta, that's like the sum of the views, right? And then so G of L theta is like the sum of those views at like those points.
Where was capital L theta? Is it? It's back way back here, right?
Yeah, it's like it's that.
This guy here? Yeah.
It's like, what's the relationship between that and like G of L?
Well, G of L theta is the result of all of the mu's that are mapped out along capital L theta.
Okay.
Okay, so capital L theta gives you this line, right? So it says everything along that line is what it's doing. So that's what, and then we have GL theta is the sum of all the mu's along that. Okay.
Oh, okay.
That was a long time ago. You remember that capital L theta. Okay. So positive angle. So here's my, I'm going to label this projection as 90 degrees, and then these are at higher angles. So they go up here, right? These measurements are at a sequence of lower angles. They're up here.
Those L with fixed theta equals 90, like lower L and higher L.
They're different L's. Yeah.
Because in the lower picture, then you change theta, right?
Yep.
In the downward right picture.
Here.
Yeah. So
Yep.
that's a different theta, but
It's same L. So here, L is always relative to like, this is 0, this is 1, or this is 0, this is 832 or something like that, right? So L is always labeling distance along my detector, okay? And so I plot that here. And so I take these data points along my detector and just map them out. L here is distance along my detector. Now the distance is a little different because it's an arc and everything, but it's still distance along my detector. So if I label this view 90, and that's the center L point, say that at the center of L, I'll say that's 90, then these are the points along my detector here, and they come in at different thetas. Because this is theta 90, right? This is theta 120, say. Right? So to get from here to here, I go from here to here. So ask the question, as I'm going from L equals my first point to L is the middle, I start at theta 120. I move to basically theta 90. So I start here and I move to here.
so sorry, the plot is
Yeah.
plotting each of the arrows, each of the.
It is like each arrow corresponds to a dot on here.
So
Right.
the theta are different. The theta in the plot and the theta equals 90 are different.
They are, right? Because the theta of each arrow is different, right? And so as I go from 90, which is here, if I'm going to march along this way, I'm going to march here to here, right? So, you know, my L is 0. So I go down to L of 0, I'm at theta 120. So it basically, if now I shift the whole thing and I rotate by 30 degrees such that now the center of L is at 120 degrees, then basically this line, this sampling line, just moves up such that its center is at 120, and it still samples a whole spectrum of angles. Yeah.
Because you get replicate data points.
It actually, you would still get replicate, quote unquote, replicate data points or up here. Like the sampling is going to be the same from here to here. It's just, I collect them in a different order, right? So I'm still going to get up here, I'm still going to get at 120, this arrow here, as I will with this arrow. It just happens that this one occurs when I'm, in this orientation. So they all get collected. They just get collected in a different order. They used to in the old days, not so much anymore. Yeah.
In the bank, but because the outer rays have to travel for a longer time, so they all travel at the same delay. All the rays have the same.
They all have the same distance to the detector. Yeah, that's correct. Now, if you had a flat detector, right, which can happen. I mean, most systems have a curved detector such that this distance is fairly constant. But you can make CT with a flat detector, but then you have to correct for the geometrical distortion of the object in your shadow because you've got these longer rays out there, right? So you can do that. You can do that correction. Yeah. On these graphs? Yeah, absolutely. So let's go from this one here. I'm going to get one projection and I'm going to measure it at theta equals 90. And L is, say, 0 here and 1 here. Okay. Oh, this L is the same L. Sorry about that. Yeah. Well, that L should be this L as well. All the little L's are the same here. And so, and this, oh, that's good. I'll correct this slide such that that L and that L look the same, right? They are the same. Yeah. Yeah. And in the function, it should be that L too. Sorry about that. Okay. So going from parallel beam to fan beam, this is the geometry. We always collect now this fan beam data, right? That's what we collect. In order to do the reconstruction, all the math you're going to see is using parallel beam data. So you have to take this data and then map it to the parallel beam data. Okay, and that you can do that by just basically resampling this data such that you get parallel beam data. So I map out a 2D function, GL theta here. I just sampled it in a different way. Now I can resample that such that if I sample all the way down here, I'm at a single projection angle and it's parallel beam data. Okay. So that geometric correction is part of the CT reconstruction when you're going from fan beam to parallel beam. And there's one of the project is show us the math and how fan beam differs from parallel beam. If you had a parallel beam scanner, would you have higher resolution than if I have a fan beam scanner? What are the differences between those two things, right? And that's it. Now, there's another thing that you have to be aware of, though, and that is because this is at an angle, if you want to do this interpolation to go to parallel beam, you're always going to get a spot here that's empty and a spot up here that's empty, right? So you need to either fill up this triangle or fill up this triangle. And to do that, you have to scan more angles such that you keep going until this whole thing fills up. Okay, and so that means you have to do at least 180 degrees of rotations plus the fan angle. got to add the fan angle to fill in that gap. Okay. Okay, so CT numbers. When we're doing our reconstruction, the thing that comes out on the, and to this day on the unit are pixel values that are in Hounsfield units. Okay. And the way you create a Hounsfield unit image is you take the mu value for that voxel that you're interested in, and you say, well, what number am I going to display? I've got this mu value. What number should I display on the scanner? And in the 70s, when they were making all this stuff up, right, they were probably using like 12-bit numbers or something like that to do this. So they scaled everything nicely such that what you do is you measure the mu value of water in your scanner that morning. Remember, we measured air. You then put a phantom and measure the mu value of water, right, in your scanner, which is, it's kind of messy, right? But anyway, as you do that, and so you know this value, and now you have the mu value that you have basically reconstructed, right, at a position. You take the difference from water and take the ratio, so it's like the fractional difference from water, and you multiply by 1,000. Okay. And that is the number that you're going to display on your scanner. And it seems kind of goofy, but it's an absolute number for that scanner. Like from scanner to scanner to scanner, because you do all of this normalization, these numbers basically replicate from one scanner to the next. Yeah.
Why do we measure it every day?
Well, if you have some kind of drift in your X-ray power, like in your tube gets old, you could have some kind of drift in the electronics on the detector, all of this kind of stuff. And it's not only, you don't do this for the whole scanner, also you do it for each detector element, right? So you get normalized numbers for each detector element, right? And so you can imagine there's some variability in how that goes. And so you normalize all that out too. So, so the mu value for water, or I'm sorry, the CT number that you would display on your scanner for water is 0. Okay, so when you put your ROI on there and you measure 0, that's water. Okay. For air, because this mu value is essentially 0, right? The mu value for air is minus 1,000. Okay. And so now we've got two things. My minus 1,000 is kind of what I'll see as the attenuation for air, and then 0 is water, and now everything else is relative to that. Okay. And to that gap between those two. And here's some values here you can look at, but it's easier to look at it this way. Here's a modern CT image. The mu value for skeletal muscle measured in this patient right here is 105 Hounsfield units. So that means mu is slightly higher than water, right? Fat is minus 120 Hounsfield units, so it's slightly lower than water. That means more X-rays get through fat than get through water. Less X-rays get through muscle than get through water. Blood with contrast in it, 650 Hounsfield units. So that means it attenuates a lot more X-rays than water. Yeah. It's about the same as skeletal muscle, about 100, between 50 and 100, something like that. Myocardium, 120. And then these little bright things down here, this is calcium in this person's aorta. So as you get older, you get calcium deposits in all your vessels, actually, but in your aorta a lot. And so that little chunk of calcium absorbs a lot of X-rays, so it's 1,300. This is a wire, right? So one of the leads, ECG leads, it gives you 5,000. So it's like way the heck up there. It gets rid of a lot of photons. Bone, cortical bone, which is this real bright stuff here, 750. So that's that stuff. If you change this is the window and level of the contrast. So what we're going to do is we're going to put the level that's the mean of what we're viewing here. We'll put it down quite low, such that all this stuff looks really bright now, but we can see the details in the lungs, which the Hounsfield unit's down about minus 800, right? So it's not entirely air. There's little tiny vessels and stuff that have contrast in them. You can see the vessels are really bright, but the lung parenchyma itself is almost air, but not quite. And up here is true air above the patient's chest, and that's minus 1,000. Okay. So that's the Hounsfield units. The nice thing about those units, right, is they're all sort of manageable integer numbers, right? So you can encode those with a few bits, right? And you know, like, whereas if you put mu values down there, you would actually have to do floating point numbers, etc. Okay, but you can, just from that formula, you can solve what the mu value would be in that tissue, right, if you needed it. Okay, we're going to go into recon. Is that 18? Am I looking at there? 16. I got 16 here. So we're going to do this because we want to get this. This is really interesting. So say we have an image and it has 4 voxels. Okay, so this is a really simple image. It has 4 voxels, and in each voxel we have a mu value, or that coefficient. So our final image will be brightness is proportional to those mu values, right? And we take the following projections. We take a projection through here, we get a G value that is mu1 plus mu2. Projection through here also, a mu value, which is mu3 plus mu4. A projection this way, G3 mu1 plus mu3, and a projection this way, mu2 plus mu4. Okay. So these are my measurements that I made on my machine. And I have 4 of them, right? And I have 4 unknowns, right? So just from linear algebra, right, then I should be able to make a matrix to invert this thing, right, and solve for these mu values given these measurements. And that's it. That's the whole deal, right? Once we have them, that there's such a thing as a sum of mu values for each one of these measurements, all I have to do is write down that big old matrix and invert it, right, to get what all those mu values are. Okay. There's a little trick here. Those of you who excelled at linear algebra will look at this matrix and say, that's not a full rank matrix, right? So basically this matrix, it turns out from those equations, you can solve, well, actually G4 is G1 plus G2 minus G3. So it's not full rank. So we actually need a new projection. We need an additional projection this way. So we did it with those 2. Now we need a third. So mu1 plus mu4 will add in here. And now this matrix actually is full rank. You can invert this and solve exactly for what mu1 through mu4 is. This problem obviously scales up, right, as the number of mu values get bigger, right? And in general, if we want an n by n image, right, then we're going to get an n squared by n squared matrix here, okay, because everything has to be written out, right? And so let's just do the example. For a 512 by 512 image, you have 262,000 rows and 262,000 columns, right? That's a big matrix. So inverting that matrix explicitly up until recently was kind of beyond what we wanted to do at all. And the other thing is, remember, these values, these p values, and we're going to have 262,000 of these things, they have noise on them. So they're not exact. So there will be, noise amplification in this inversion process and stuff. And so usually this is not the way reconstruction is done, although it can be if you use some tricks for inverting really large matrices, etc. Yeah. We can't. With one measurement, we only know the sum. Well, no, we're actually taking it into account because we do know these algebraic relationships are true. We don't know, like, we have their total, but we don't know their individual values just by one measurement. It could all be in mu1, it could all be mu2, right? So So we'll take a look at that when we look at simple back projection. Okay, great. That's it. Sorry, I went over 2 minutes.